Hello and good day. This is Mr. Traxler, and today we'll be talking about second differences with quadratic equations. All right. So let's just do a starting warm up. So this will really help us get familiar with some ideas that are fairly simple but are pretty important for what we'll be talking about. Now, to start off with, we're just going to be adding up the odd numbers. Just a real basic idea that has maybe some interesting patterns that you might not have noticed before. So to start off, you just start with 1, the first odd number, and then you would go to 1 plus 3, and so on. All right, so go ahead and pause this video, and what I'd like you to do is see what pattern you notice when you do this. Okay, great. I'm sure you found at least one kind of interesting pattern. Let's take a little bit of a closer look at that. Okay, so we start with the first odd number, which is 1. Then we go on to the second odd number, which is 3. We add that on. What do we get? 4. We add on the next one, 5, which gives us 9, and so on. I think we're already starting to see a pattern, especially with this visual cue. What is this function? What do we call it? What would we call it? Well, you might call it the square function because you're squaring each time. You might call it y equals x squared. All right. So take a look at those column headings. You'll notice those are the number of odds. And then on the right, that's the sum. In other words, if we add up those odds. Let's go ahead and relabel those. All right. So the first one we're relabeling x. The next one we're labeling x squared. Okay. So we're dealing with the function x squared. Okay, so this is where we start talking about the star of today's show, and that is our differences. So first differences, surprisingly enough, you're pretty darn familiar with already. Now why? Because when you learn about first differences, that's the only difference you really know about. So we just call them differences. What are differences? It's how far two things are apart, what you have to add to get to that next object. So from 0 to 1, what's the difference? Just 1. And then from 1 to 4, it's just 3. 4 to 9 is 5, and so on. So you might notice that that looks familiar. Yes, it's on the left. Those are the odd numbers we added up. So in the case for x squared, that can be thought of in terms of its first differences. The first differences are a little bit like rate or speed, are the odd numbers for x squared. Okay, so we are going to be investigating some important properties, not of first differences, which once again you know quite a bit about, but second differences. All right, so let's investigate that. What are second differences? Pretty simple. It's just the differences of the first differences. You just do the same thing you did before, but you do it that second time. All right, and we see if the pattern shows up. See if we can figure out what this pattern is. Pretty simple one. You just add 2 each time. All right, so what this tells us is that there seems to be some kind of connection between something like x squared and second differences. All right, so we'll investigate that further. We'll talk more about that connection. All right, and you might be able to get a clue a little bit about what the connection is just by looking at this picture. All right, so second differences, by the way, while cool shapes like this is important, for what we're talking about today, second differences, once again, are really what's most important. All right, so let's do something else. This looks a lot different, right? This looks like a totally different problem, lots of crazy numbers. What is going on? All right, so what I'd like you to do is once again pause this video and see if you can find some patterns. All right, I'll start you off in case you have no idea what I'm talking about. First, you may want to come back to the second row, because as you can see, there's a lot of decimal numbers in there. It can be a little bit complicated. You may want to come to that one last. The first one, a pattern I notice right off the bat, is it seems to go up by 1 each time. Okay? All right, so go ahead, pause that video. All right, good job. I'm sure you found some pretty cool patterns. And extra good job if you managed to decide what was on the patterns for the second row. All right, so the first row, we're going to investigate these patterns more on the next page. So we'll see how many of your predictions come to fruition. All right. So first, I'm just going to label this one something really, really kind of disappointing. These are just the numbers, but for how I'm going to think about these for now, that's because these top numbers, they're pretty simple to begin with, help to explain how I'm thinking about these others. So you'll notice that second row, well, I said it was tough, right? So you might have gotten an intuition and checked it that yes, the second row is just the square of the first row. And then what's the next row? Well, they're the first differences. Other patterns abound, I'm sure, but that's the main one. And then there are the second differences. So we're starting to see some similarities to this and the previous page. Let's see if we can find any other similarities. Okay, this is what we saw before on the previous page. All right, so in case you forgot, now we're going to start to overlay some of this with some of our new information. Okay, so one way to think of squaring stuff is, and by the way, these marks aren't quite at the right spot. Forgive me for that, but that's pretty close to the 0.4 mark. So if you square the first square is going to be about that area. In other words, it's going to be the square of 0.4 length. All right, and so then this, so you'll notice it goes a little beyond. 1.4 is, of course, longer than 1, so it's going to go beyond that first square. And that area is going to be 1.96. None of these numbers have even been on the first page, except, of course, the 2.4, which, if you recall, lined up with 5.76. 3.4 lines up with 11.56, and so on. So we were actually dealing with the same problem, y equals x squared. It's just that we had different inputs. All right. But let's see how could we have known that without this awesome picture or just having it just come to us? So insight is great, and that's partly why we're here. But how could you know it was x squared for sure, even if you didn't know that? So we'll at least begin to answer that question in this video. It may seem like we answer it, but I would say we at least come close. All right, so first, once again, instead of saying square length, we're gonna make it simple, like we like to do in math, and just replace that with a single letter. And square area is, of course, x squared. Let's talk about first differences. So let's see if we can see any other commonalities between this and the previous page. Okay. Every number on the left is added 0.4. And the first differences, they look similar, but not quite. What about second differences? Exactly the same. The second differences are exactly the same as they were in the previous table. This gives us further evidence. We're starting to think y equals x squared must have something to do with second differences too, and it does, and it's really cool. So, and it's something you'll look at in the most depth in calculus, but we'll get at least some depth for that right now. Okay, so I'm gonna replace x squared with y, just because that's usually the column name that we use. That's y is x squared in this case. Now, real quick, I just want to introduce some other ways you can think of first and second differences to bring it down to earth. So it's already hopefully a little simple. You worked with differences and subtraction before. First difference is often called the change in y. Now check with that. Pause it for a moment if you need to. Does that make sense? Why would it be called the change in y? And in fact, that's usually what it's going to be called. It's usually going to be called the first change in y instead of first differences. It might also be called, in a real-world situation, average speed. All right? Might be called average speed. Like the speedometer gives you something very similar. It gives you instantaneous speed. All right. So wow. So if an object was mapped by x squared, then here right here would be the average speeds at different times between 0.4 and 1.4, for example. The average speed is 1.8. If this was, for example, how many seconds had passed or something like that. All right. So what about second differences? What would that be called besides just, well, the change in the first difference, the change in speed? Oh, wait a sec. That gives us a hint, doesn't it? So what is change in speed? Have you ever had a real life situation where your speed has changed? What is that called? What happens if you're in a car and your speed goes up? What do we call that? Well, there's just the colloquial idea of acceleration, but it turns out second difference is the precise, or at least very close to the precise physics definition of acceleration. This is really average acceleration, but for something like x squared, it doesn't change. So it also somehow happens to be the instantaneous acceleration. So second difference is pretty darn close to the same as acceleration. If not quite, if we're being super technical, but it's pretty close. All right, very cool. You now know pretty much exactly what acceleration is. If you drop a ball, that's acceleration. And it actually is modeled very well by a function much like x squared. Much like a quadratic, modeled by a quadratic equation, assuming you're not taking in crazy things like air resistance. All right, awesome. So that's one of the most awesome things about an equation like x squared, by the way. Among them are many. All right, so what are the first and second differences of the function y equals 3x plus 5? So we're taking a much simpler one just to see what does it look like with stuff we're really real familiar with, like y equals 3x plus 5. That's just, at least most people think, is simpler than x squared. Well, let's go ahead and film this graph. We know how to do that. You just plug in those x values. Okay, what are the first differences? Oof, well, geez, I see why we don't work that much with first differences before we see x squared, because that was kind of boring. Maybe second differences is less boring, about equally boring. Okay, so it's just a constant rate. So first differences, okay, looks like it has something to do with slope, right? All right. And then second differences says that there is no change in speed. So it means this function must have a constant speed. Okay. All right. So interesting way to look at this function. But we're sort of looking at this as a non-example as much as anything. Something that doesn't have x squared in it. And it's also something that doesn't have a change in speed. All right. Let's ramp up the intensity. We're going to just add 3x squared. So that's pretty much all we're doing for intensity. Don't be intimidated. This will take a little longer to fill out the table. See? It's taking at least a third of a second more for me to hit that forward key. I told you it would take a little longer. But other than that, is it going to be much different? Not really. Let's calculate the first differences. What's it take to go from 11 to 9? Don't say 2. It's negative 2. And then 4, 10, 16, 22. So what do you have to add to 11 to get to 9? That's right, it's negative 2, even though I know 2 is very tempting to say. All right, so wow. So we started off with something really complicated. Do we bring it down to something simpler come out when we do second differences? Whew, it does. All right, interesting. So we get a 6. I wonder where that 6 came from. I wonder if it has anything to do with, maybe that 3 there, because I think 6 has something to, that's related to 3. It has something to do with something up there, right? Maybe it has to do with adding up what's up there. Who knows? It has something to do with that equation, right? How could it not? There's a 6 there and some numbers that are probably related to 6. All right, so let's see if we see any patterns that might tell us probably what's going on. Well, I'm noticing that there's a pattern between what's in front of x squared and then, ooh, that didn't quite show up right. Okay. And what's in front of x squared, which for y equals x squared, that's sort of like 1. For what's in front of um,